This presentation summarizes a groundbreaking paper on the phenomenon of model collapse in AI systems. Model collapse is a degenerative process affecting generations of AI models. When models are trained on data generated by their predecessors, they gradually lose the ability to perceive the full range of the original data distribution. Model collapse occurs due to the three main sources of error: statistical approximation from the finite sample, limitations in the model's ability to express complex functions, and errors in the learning process itself. Statistical approximation error is the most fundamental, occurring simply because we're working with a finite number of samples. It's unavoidable in practice, but can be mitigated with larger data sets. Functional expressivity errors relate to the model's architecture. It's about whether the model is theoretically capable of representing the true distribution, regardless of training. Lastly, functional approximation errors are about how practical the training is. Basically, how we actually get the model to learn. It includes issues like getting stuck in local optima or biases in our training algorithms. All three types of errors can compound over generations of models, leading to the progressive degeneration described in model collapse in this paper. Theoretical analysis shows that both discrete and continuous distributions are susceptible to model collapse. Over time, the model's output tends towards a single point or very narrow distribution. If we look at these two graphs, the first being discrete distribution, we can see that the bar chart shows how a discrete distribution over categories A, B, C, and D changes over the three different time points labeled T1, T2, and T3. T1 being in red, T2 being in green, and T3 being in blue. Initially, we can look at T1. The distribution in T1 is relatively uniform across all categories. Over time, T2 and T3, you can see that distribution becomes more concentrated on category C. This narrowing represents increased certainty or focus on a particular category as more information is gathered or processed. When we look at multi-dimensional Gaussian approximations, we can use a scatter plot that represents a 2D projection of a multi-dimensional Gaussian distribution at 3 time steps. Again, the time steps are labeled in the same color. The size and color intensity of the points represent the probability distribution. At T1, the points are widely dispersed throughout the whole table and indicates high uncertainty. By T2, and especially by T3, the points become more concentrated in a smaller region, showing reduced uncertainty and a more focused distribution. The researchers conducted experiments using the OPT-125 language model. They fine-tuned it on the Wiki Text2 dataset and then on data generated by previous model iterations. The OPT-125M language model is a language model with 125 million parameters. It's much smaller than models like GPT-3 that has 175 billion parameters. And the WikiLeaks language modeling dataset is a collection of over 100 million tokens extracted from the set of verified good and featured articles on Wikipedia. And this slide helps to kind of show how the model was put together. The experiment showed that models trained on generative data could learn some aspects of the original task, but with increasing errors. Performance degraded over generations, especially when no original data was retained. These graphs demonstrate the effects of model collapse by showing how the perplexity, a measure of how well the model predicts the sample, changes across generations. Lower perplexity generally indicates better performance. And when we look at these models, you can tell the top set of graphs show where no data was preserved over 5 epochs. And the second set shows where 10% of the data was preserved in 10 epochs. And you can see overall that the perplexity levels are lower than in the group where the data was preserved versus where there was no preservation of past data. So the key takeaways from these graphs are that model performance degrades across generations as shown by increasing average perplexity. The distribution of perplexity shifts and spreads out, indicating that while some outputs become more probable, others become much less probable. And then we do retain some original, when retaining some original data and using more training epochs, it helps to mitigate the degradation, but doesn't prevent it entirely. As generations progress, the quality of generated text did decrease. Later generations produced text with more repetitions and less cohesion compared to earlier ones. And these are different examples of the original, an example of the original input and 4 different examples of the different output, including the very first in generation 0 to one of the later, the last in generation 9. This research highlights the importance of maintaining access to original human-generated data. Relying too heavily on AI-generated content for training future models could lead to degradation for AI capabilities over time. Moving forward, the AI community needs to address challenges such as tracking the origin of training data, ensuring AI models can represent diverse viewpoints, and finding the right balance between efficient at training and maintaining data quality. In conclusion, this research reveals a critical challenge in the long-term development of AI systems. To prevent model collapse, we must ensure continued access to diverse, high-quality human-generated data in our training processes.